everyone, my name is Delima. Come join me as I go through 5 practical physics experiments in this video. Starting with the first experiment, that is experiment DC1, measuring the internal resistance and the position of a galvanometer. This experiment have 4 sub-experiments, that is DC1A, B, C, and D. So let's get to it. In this DC1 experiment, we studied different ways to understand how galvanometers and basic electrical circuits behave. First, we measured the internal resistance inside a galvanometer using a potential divider circuit. Then, we calculated its sensitivity, how much current is needed to move the needle. After that, we explored how resistance readings can change depending on how a voltmeter is connected, either with a resistor, an ammeter, or with a resistor only. These experiments help us understand how current, voltage, and resistance interact in real circuits, and how even small changes in setup can affect results. And here are the apparatus needed for all 4 experiments. And this is a detailed version of DC1A experiment, which we measured the internal resistance of a galvanometer using a potential divider circuit. We used known resistor values and recorded the current before and after adding an extra resistor. Using the formula, we calculated the internal resistance of the galvanometer based on the drop in current. Here's how one of the DC1 circuit is set up for the experiment. In DC1B, we tested how sensitive the galvanometer is. We increased the resistance slowly to get full-scale deflection and used the voltage, resistance, and deflection values to calculate the current. Then, we found the sensitivity by dividing the current by the deflection. For DC1C, we connected the voltmeter in parallel with both the resistor and ammeter. This setup caused the voltage reading to include the ammeter's internal resistance. We calculated the actual resistance by subtracting the ammeter's resistance from the apparent value. In DC1D, the voltmeter was connected directly across the resistor only. Since the voltmeter draws a small current, the ammeter shows slightly higher current than what actually flows through the resistor. We used a correction formula to find the true resistance and reduce the error. These are the results and data from my experiment. So in conclusion, all 4 DC1 experiments help us understand how a galvanometer works and how resistance is measured in a circuit. We learn how to find the internal resistance and sensitivity of the galvanometer and how different voltmeter placement can affect resistance readings. These experiments showed that accurate measurement depends on proper circuit setup and awareness of internal instruments effects. Next, for our second experiment is experiment M2, which is rigidity modulus of wire by using Maxwell needle method. Its objective is to determine the modulus of rigidity of a wire using the Maxwell needle method, and this is a detailed introduction of it. And this is apparatus and the experimental method. This experiment uses the Maxwell needle method to determine the modulus of rigidity of a wire. The wire is twisted and allowed to oscillate, and the time period is recorded for 2 different mass configurations. By analyzing the change in oscillation time with respect to wire length, we can calculate how resistant the wire is to twisting. So this is my data and results from this experiment. The modulus of rigidity of the wire was found to be around 68.2 gigapascal, which is close to the standard value for steel. This shows the experiment was mostly accurate. Some small errors were present, but overall the results support the theory. Next, our 3rd, 4th, and 5th experiments were conducted in a dark room to reduce interference from external lights, starting from experiment O2, refraction of light. This experiment is to measure the refraction and dispersion of light through prism to examine the characteristic of light through a prism of different medium density and to determine the angle of refraction of light through prism. This is the apparatus and experimental method that were used. We investigated how light bends or refracts as it passes through a glass prism. Using a sodium light source and a spectrometer, we measured the prism angle, observed how white light splits into colors, and recorded the angle of minimum deviation from different wavelengths. This helps us understand the behavior of light in different mediums. This is the results that I get, and from the results, we saw that the shorter wavelengths like violet light bend more, while longer wavelengths like red bend less. The graph showed a clear trend matching theory. Through some values like the prism angle had large errors due to manual readings, overall the experiment proved how prism refracts and disperses light accurately. Next, our fourth experiment, that is MP1 photovoltaic cell, which to find the relations between current with distance and between current with cosine angle. Using the apparatus and the experimental method, we explored how a photovoltaic cell converts light into electricity. The aim was to find the relationship between the electric current and two factors, the distance from the light source and the angle at which light hits the cell. We used a microammeter to measure current under different setups and plotted graphs to study the patterns. The results show that current decreases with increasing distance following the inverse square law, and also decreases as the angle increases following the cosine law. This confirms the theoretical behavior of light intensity and photovoltaic response. Some errors were observed due to human reading and setup limitations, but overall the results supported both laws quite well. Last but not least, our experiment 03, that is diffraction grating. We learned how to use a diffraction grating for producing spectra and measuring wavelengths, also to study the continuous spectrum and to calculate the grating constant. Here are the apparatus and the experimental method, which contain two parts, that is to study the continuous spectrum and to calculate the grating constant. In this experiment, we use a diffraction grating to study the spectrum of light and measure the grating constant. We observe how light from a frosted bulb and a mercury lamp splits into different colors. Using the angle of diffraction and known wavelengths, to calculate the number of lines per millimeter of the grating. Finally, we obtained a grating constant which had a 21.3% error compared to the actual value. Although some inaccuracies were present due to angle reading and setup alignment, the spectral pattern and color order still matched theory. This shows that the experiment worked and confirmed the basic principle of light diffraction. That is all from me. I hope you enjoyed the video. Thank you for watching. Bye bye.